Continuing on from the video about combustion equations and how to balance them, we're now going to think about why these are actually useful. Why do we want to be able to balance equations in the first place? So if you've not seen the video on combustion equations, watch that first, then come back to this one. So we want to think about how to use balanced equations. Now, what does that mean? That means, can we use the mole ratio that we have found in the balanced equation? That means the number of moles to the number of moles on each side, or comparing different numbers of moles depending on what's the reactant, what's the product, and so on, how many of each we have. Can we use that to figure out amounts of substances? Do we figure out how much we've used of something or how much we've made of something else? And the answer is yes, of course we can. That's why they're so useful, and that's why it's such a key skill in chemistry to be able to balance an equation. So for example, if I take this very common equation, this is the equation for the Haber process, which you'll learn about in Unit 3, and it's when we take nitrogen gas and hydrogen gas and we produce ammonia. Now, this equation is not balanced because I do not have the correct number of atoms on each side, so we're going to have to balance this before we start. So we have 2 nitrogens here and only 1 here, and we have 2 hydrogens here and 3 here. So we'll start with the nitrogens, 2 to 1, we want 2 to 2. So let's multiply that whole thing by 2. Remember, we can't change the little numbers. So that's the nitrogens now balanced, but now we have 6 hydrogens over here and only 2 here. So we're going to have to multiply this 2 by a 3. And now we're all balanced. 2 nitrogens on each side, 6 hydrogens on each side, and we're good to go. So what does that actually tell us though? Well, it tells us that for every 1 mole of nitrogen gas, of which there are 2 atoms contained within, per molecule in 1 mole, and I add 3 moles of hydrogen gas, each molecule containing 2 hydrogens, I will produce 2 moles of ammonia gas product. And that will become very powerful, very useful in calculating things, because we can then carry that ratio through to apply to different numbers. Okay? For example, if I instead have 2 moles of nitrogen, maybe I don't have exactly 1 mole, maybe I have double. Why is that useful to know these numbers? Because for every 1 nitrogen, I have 3 hydrogens. For every 1 nitrogen, I have 2 ammonias. For every 3 hydrogens, I have 2 ammonias, etc. I can use these numbers however I want. So if I've multiplied this 1 to 2, I've doubled it. Which means this number gets doubled and this number gets doubled. So for every 2 moles of nitrogen, I will have 6 moles of hydrogen gas and 4 moles of ammonia. And this can work with any number you like. So what if I have 0.25 moles of nitrogen? Well, whatever I do to this number, I have to have 3 times it of hydrogen and 2 times it of ammonia. That is what my ratio tells me. 1 to 3, 1 to 2. So if I go 1 to 3, I need to times this by 3. So it's 0.75. And if I go from here to here, I need to go 1 to 2. So this times 2 is 0.5. So that way I can very quickly work out, without doing any experiment, if I have 0.25 moles of nitrogen, I will produce 0.5 moles of ammonia. And that is very, very useful, because we can then use this number of moles to work out, say, a concentration or a mass or a volume or something more useful that we can actually use in an experiment, and that's fantastic. So that's what we want to say. This is incredibly useful because this can be used to calculate amounts of substances either used or produced in a reaction. So what we're going to do is take our time and look at an example in detail of how to do that, because at National 5, this is quite an involved process. It's actually a 5-step process and usually a 3-mark question. So it's one that if we're good at, we can get a lot of marks out of, but there's a few steps that we need to remember. And those steps are always the same. So if we remember them, we'll be on to a winner. So this question asks, calculate the mass of water produced in the reaction of 3.2 grams of methane, CH4, with excess oxygen. Now before we start, before we look at the process, we are 1, given a balanced equation, so that's good. 2, we know that this is a calculation because the word calculate has been used. That will keep us right. We know we are interested in the mass of water and methane. And it says excess oxygen. Now, excess oxygen simply means there is plenty of oxygen for all of my fuel to burn. So I know that I use 100% of my methane. That's all that that's telling me. We can ignore that for just now, as long as we remember what that excess just means there's plenty of oxygen, so that's good. So what do I actually have to do? Well, there's 5 steps, and to remember those 5 steps, we're going to think about RIT-RIF, so RIT-RF, and we're going to fill in what those mean as we go on through the video. So, first step, we want to come up with a mole ratio. And that is dead easy, because all we have to do is look at the big numbers in our balanced equation. So if there's no number in front of the compound, it means there's one of them. And if there's a number, then there's that number of moles. So what this balanced equation is actually telling me is that there is 1 mole of methane reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide, because there's no number here, and 2 moles of water. That's what that balanced equation is actually telling me. So that ratio is what is going to be very useful. So the I in RIT-RIF stands for info, and by info we mean info from the question. So what are we told? Well, we have a value here for methane. So we're actually interested in this chemical here. And we know that we're trying to find the mass of water. So it's going to be this chemical that I'm also interested in. Now that's just made our life a lot easier, because we can effectively now ignore the middle 2 chemicals. We don't need them, because we have this ratio. We have this 1:2 ratio, and that's important. Now what else are we told from the question? The mass. So we're going to write that down underneath the chemical that it's important to. So we have the mass is 3.2 grams. So that's all of our info noted down. The T stands for triangle. We're now going to have to use one of our formula triangles to make this number into a more useful number. Because we have a mole ratio, we want to be working in moles if possible. That makes our life easier. So how are we going to get a number of moles from a mass? We're going to use the GFM, because we know that the number of moles equals mass divided by GFM, and that's from page 3 in the data book. So we're going to have 3.2 divided by 16. And if I work that through, that is going to give me 0.2 moles. Okay, so that's the triangle done. So what is my next step? It's a second R. So what does that mean? That is another ratio. Now what do I mean by that? I mean I actually have to use the mole ratio from the equation this time. So I have not 1 mole, as the equation states, but I have 0.2 moles. So how am I going to get how many moles I actually produce of water? Well, I'm going to say for every 1 mole of methane, I produce 2 moles of H2O. So I have to multiply whatever I have of methane by 2 to get to water. So if I have 0.2, I have to multiply that by 2 because it's a 1:2 ratio, and I will get 0.4 moles. So that equals my N on this side now. So we're nearly there. All we have to do is give a final answer, and that is what the RIT-RIF F stands for, in the format that it's asked for. So if we go back to the question, it asks for a mass of water. So we want to now convert that number of moles into a mass. And how do we do that? Well, very easily. We just note down our new GFM for H2O, which is going to be 16 from oxygen, plus the 2 lots of hydrogen that we have in our molecule, which is 2 times 1. In total that is 18 grams. And if we use our triangle properly, we will find that we have the mass is equal to the number of moles multiplied by the GFM. So that is going to give us our found value of 0.4 times 18, which in this case is 7.2 grams. And that is our final answer, 7.2. So, using RIF, using those 5 steps, we have found a ratio. We've written down the relevant information from the question. We've figured out a number of moles. We've used that mole ratio from step 1 to figure out the number of moles of the thing we're interested in. And then we've used that number of moles to work into a final answer that is required for the question. Now, if you are quite happy with that method, then that is the method you should use. That is the easiest method. However, like most things in chemistry, there's actually a second way that we can do this, and that is by proportion. And this is actually quite useful for moving on to higher and advanced higher level 2, because it's quicker and it doesn't require us to use the triangle. It just requires us to use the GFMs. So what am I talking about here? Well, if we use that same ratio, which we always have to figure out, that is the most important part here, using the balanced equation. That's why it's called using a balanced equation. And we can actually just use the GFMs. So for methane it's 16 grams, for water it's 18 grams. Multiply by however many moles we have. So 1 times 16 is 16. 2 times 18 is 36. And say to ourselves, well, if 16 grams produces 36 grams, which is 1 mole produces 2 moles, then 3.2 grams, which is what we have, will produce X. Right? So all we have to do is figure out, well, how do we get to X? Well, we say to ourselves, what have we done to get from 16 to 3.2? Because whatever we've done there, we can just do the same to the other side. It's kind of like a shortcut to the answer. So to get to 3.2 from 16, I have had to divide by 16 to get to 1, and then multiply by 3.2 to get to 3.2. So that is exactly what we're going to do to the 36 to get to X. So X equals the 36 multiplied by the 3.2 divided by the 16. And you can think of that as a sort of cross multiplication as well. So this times this equals this times this, and then I take the 16 over the other side and divide by it. Or 16 divided by 16 gives me 1, times by 3.2 gives me 3.2. 36 divided by 16 and then times by 3.2 is what we've done to this side, so we have to do it to this side. And that, if we work that through, will give me the exact same answer. So if you're good at maths, or you prefer to do things by equations like that, then maybe that would be a better method for you to try and practice. If not, you really don't have to worry about this way. You can just focus on the 5 steps, figuring out the ratio, filling in the information from the question, using the triangle, using the ratio to get to the other side, and then figuring out the final answer.